All right, for today's video lesson, we are going to be learning about position, velocity, acceleration, and time relationships for objects that are in simple harmonic motion. All right. So hopefully you guys have taken the time to watch these 3 videos to kind of visualize what is occurring for a mass that is oscillating on a vertical and horizontal mass spring systems, as well as a pendulum experiencing simple harmonic motion as well, okay? These 3 videos are really helpful to reinforce kind of the topics that we have been discussing and also allow you guys, again, to visualize what is occurring. Okay, so for today's topic, we are, as I mentioned, we're doing position, velocity, acceleration, and time relationships for objects in harmonic motion or oscillatory motion. Okay, so let's look at this image on the left here. So we have a spring that is going to oscillate up and down. Okay, at the equilibrium position, this is where it will be if it's not either compressed or expanded. It's just going to be like where it's happy right here, okay? Now, as it moves up and down, we can identify those changes by change in X. So as it goes further downwards, we'll say that is in the negative X direction. And as the spring compresses, we'll say that is in the positive X direction. So this first of 3 graphs we're going to look at here, this is the position on the X-axis, and this is just the time as the object oscillates. Okay, so up here, this is where the spring is compressed. As we let go, it's going to go down to the equilibrium point, go down to negative X, so right down here, and then it is going to come back up to the equilibrium point, to the compressed point, and then that is going to continue. So for one whole wavelength, that is 1 period. So from crest to crest, so from here down up to the crest again, that is 1 wavelength there. And the height of that is going to be its amplitude, okay? That is a new term for us, amplitude. So that's just saying that the displacement of the mass is going to be the amplitude now, okay? The next graph we're going to look at is the velocity graph. So note that the max velocity is actually occurring where the position is right at the equilibrium position. This is because that is the fastest that spring is going to be moving. As it moves up, it's going to slow down. And then as it comes down, it accelerates. And then when it gets to the bottom, it's going to, again, start moving back up. So we'll have maximum velocity when that mass is at the equilibrium position. Okay, our max acceleration is going to occur when either the spring is at the furthest point, right? Because as it comes down, it's going to accelerate faster back towards the equilibrium position, okay? So what you need to take away here is that the velocity and the acceleration are going to be different depending on the position of that mass on a spring. All right. So for acceleration of a mass on a spring, as a mass bounces back and forth, it will have a changing acceleration. The changing acceleration occurs because the restoring force is always changing, right? Remember, the restoring force is the force that wants to bring the displaced object back to its equilibrium position. Okay. In our examples, we are going to only examine frictionless situations. So in these cases, there are not going to be any other forces to consider. So the net force will just be the restoring force. So the net force of the movement of the spring is going to be the restoring force. Okay, so we could say that in an equation as F net is equal to Fs. So that's going to be the restoring force in a spring system. We know from previous unit that F net is equal to mass times acceleration. And from this unit, we need to know that the restoring force, Fs, this is on our formula sheet, that is equal to Kx. So we're just doing another formula substitution here. Okay, if we isolate for acceleration, so if we are looking for the acceleration of a mass on a spring, we'll just isolate for A, so we'll divide both sides by M, and then we'll be left with A is equal to negative kx over M. So remember, K is the spring constant, X is going to be the displacement of the mass, and M will be the mass of the mass, of course. Okay, this formula is not on your formula sheet, so you will need to know how to get from F net is equal to Fs to isolate for acceleration in a mass spring system. All right, so let's look at an example here. All right, there we go. All right, so our first example here, we are determining the acceleration of a 0.250 kilogram mass at the end of a spring, which has a constant of 54.9 newtons per meters. Okay, so let's just write our variables down so we know the mass is equal to 0.250 kilograms. K is our spring constant, which is 54.9 newtons per meter. And its displacement, X, is going to be 12 centimeters. If we divide that by 100, we will find that it's 0.12 meters. So stretched, I'm going to assume that it's going to the right. And then to the left is negative. All right, so we are looking for the acceleration of that. So because this is a frictionless system, the only forces to consider is going to be the net force, and that is going to act as the restoring force. So the net motion of that mass is going to be responsible for the restoring force, so Fs. From our formula sheet, we can expand this, so F net is equal to ma, and the restoring force is equal to negative kx. Okay, so we are looking for the acceleration, so let's divide both sides by m. Now we have A is isolated, so acceleration is equal to negative kx over m. Now that that is isolated, we can go ahead and solve for A. So A is equal to negative, K is 54.9 newtons per meter. X, the displacement of the mass, is 0.12 meters. And we're dividing that by the mass. All right, so if you punch those into your calculator, you should get a value with sig digs. There should be 2. Will be 40. Sorry, acceleration will be negative 26 meters per second squared. So negative acceleration, does that make sense? Well, yes, because remember, we stretched it to the right. So the restoring force is going to be acting to the left because it wants to go back to that equilibrium position. This is to the left. Okay. So again, the big thing here is making sure that we're able to go from F net is equal to the restoring force and able to isolate for acceleration there. Okay. Okay. Okay, so that was acceleration of mass on a spring. So now we're going to talk about velocity of a mass on a spring. Okay, so in the previous examples, the mass has just been released from rest. Okay, so remember, like if we're up at the top, right before we leave it, the velocity is going to be 0. Now, as it accelerates, so we're in a mass spring system, so it's going like this. So right before we let go, velocity is 0. As we let go, the acceleration is going to, well, it's going to accelerate as it goes back to the equilibrium point. And the elastic potential energy that was stored in the spring back here is being converted to kinetic energy as the mass goes faster and faster. At the equilibrium point, there is no more elastic potential energy remaining because it all has been converted to kinetic energy. So at the equilibrium point, we will have a maximum kinetic energy. So the furthest point that the mass is from the equilibrium is called the amplitude of a spring. Okay, so this is a new term. If we want to calculate the maximum velocity of a mass on a spring as it passes through the equilibrium point, remember that is where the maximum velocity is found. When it's released from a certain amplitude, when we know the displacement of it, we can use our knowledge of the conservation of energy to help us solve this problem. Okay, so I hope that this is not scary to you, but we're going to talk through it anyways. Okay, so this is just saying that the mechanical energy is going to be conserved in a system. Okay, if we expand mechanical energy, remember mechanical energy is equal to the kinetic energy plus the potential energy, and that is going to remain the same in the system throughout. So on the left here, this is where our kinetic energy is 0. So that's right before we let go of it. So at that point, we have maximum potential energy and 0 kinetic energy. Now, on the other side of that, at this point, this is where the equilibrium position is. We are saying that the potential energy is equal to 0, and it is all kinetic energy at that point. Okay, so that's how we get to here. Now we can substitute the potential energy of a spring is 1/2 times kx squared. Okay, you will find that on your formula sheet. And we know that the kinetic energy, we can substitute that with 1/2 mv squared. Okay, now for the next step, we're substituting x for amplitude. Okay, remember the amplitude of something in oscillatory motion can be the same as the displacement. So we're just substituting x for a there, and we're leaving this one alone. Okay, because we have 1/2 on both sides, we can cancel 1/2. So we'll be left with ka squared is equal to mv squared. So remember, k is the spring constant, a is the amplitude, m is the mass, and v is the velocity. So if we isolate for velocity, we'll divide by m on both sides. We'll be left with v squared max is equal to spring constant times the amplitude squared divided by m. If we take the square root of both sides, we will get rid of the squared here, and we will be left with v max is equal to the square root of ka squared divided by m. If you take the square root of a squared, it will just be a, and we're going to leave k and m underneath the square root because we cannot simplify that. Okay, this is how this formula is derived. I just wanted to talk through that with you. This is on your formula sheet here. V max is equal to a times the square root of k over m. Okay, so you don't need to know how to get to this process, but I just wanted to discuss that with you guys. Okay, so V max is equal to the amplitude of the mass divided by the square root of the spring constant divided by the mass. All right, so let's try solving a problem with that. Oops. Okay. I just realized that I skipped example 2. It is very similar to example 1, except for we have a negative displacement instead, okay? So try that one on your own. If you need help, I'd be more than happy to go through that with you. Okay, but we're just gonna jump ahead to example 3 here. So we have a mass of 17 kilograms, so is pulled 13 centimeters away. So in this case, remember, the displacement of x is going to be replaced with the amplitude. So that is going to be 13 centimeters. And we want to convert that to meters. So divide that by 100, give us 0.13 meters. We know that K is 367 newtons per meter. So we are looking for the max velocity. Okay, so using the formula that we just talked about on the last slide, we know that V max is equal to the amplitude multiplied by the square root of K divided by M. We have K, we have the amplitude, and we have the mass, so we can just go ahead and substitute that in. So V max is equal to 0.13 meters multiplied by the square root of K, which is 367 newtons per meter, divided by the mass, which is 17 kilograms. Okay, so if you punch those into your calculator, you will get a value of 0.60 meters per second. Okay. Hopefully that's all right. Okay. So that was example 3. All right. So period of a mass on a string. Oops. Okay. So period of a mass on a string. So simple harmonic motion can closely resemble circular motion. So two conditions are going to be necessary if circular motion is used to replicate simple harmonic motion. So if the period of the circular motion and the simple harmonic is the same, then we can replicate circular motion as simple harmonic motion. Secondly, the radius of the circular motion must match the amplitude of the oscillator. Okay. So let's just go ahead and talk about this. So period of a mass on a spring. So we'll start at velocity max is equal to velocity max. Using simple harmonic motion, we know that velocity max is equal to the amplitude multiplied by the square root of K, the spring constant, divided by M. Now, if the period is the same and the amplitude is the same, then we can substitute in our circular motion formula for velocity. So 2 pi times the amplitude over t. Okay, so if we simplify that, we can cancel a because it's on both sides. And we're trying to find the period of a mass on a spring. So we'll multiply both sides by t and then divide by k over m to isolate for t. And then if we simplify this, so t is equal to 2 pi divided by the square root of k times n. This is the equivalent of the reciprocal of that. So instead of dividing by k divided by m, you can multiply by the reciprocal of that. So just flip the numerator and the denominator. So period is equal to 2 pi times the square root of m over k. Again, this is on your formula sheet. I just wanted to show you how we got to that formula, okay? T is in period, units of that is second, m is in mass, kilograms, and k, again, is the spring constant. All right, so example 4. We have a mass of 17 kilograms. The amplitude is equal to 13 centimeters, which is equal to 0.13 meters if we just divide by 100. Okay, we know the constant is 367 newtons per meter, and we're looking for the period. Okay, so from our formula sheet, we will find that period is equal to 2 pi times the square root of m over k. We have m, we have k, and we know pi, so we can just go ahead and solve this now. So 2 pi multiplied by the mass of 17 kilograms divided by the spring constant, 367 newtons per meter. Okay, be careful when you're entering this into your calculator. Make sure you take the square root of 17 divided by 367 and then multiply by that. Okay, so just be careful with our brackets there. So if you punch those into your calculator and round with sig digs, you should get a value or a period of 1.4 seconds. Okay, perfect. Okay. So the period of a pendulum is what's next. This is going to be our last topic for today. So one thing you might be surprised to know is that the mass attached to the end of a pendulum does not actually affect the period of the system. The only thing that a heavy bob does, remember bob is the thing that's at the end of a string, just a general term. The only thing that a heavy bob does is keep the pendulum going for a longer period of time because it has more momentum, right? What really matters when trying to find the period of a pendulum is actually the length of the pendulum and the force of the gravitational field surrounding it. Okay, so T is the period of one whole swing. So as it goes back and forth, right? So if it starts here, if it goes there, and as it comes back here, that is one full period. That's one whole oscillation. Okay, length L, fancy L is going to be the length of a wire, and G is the acceleration due to gravity. So with this, if you know the period of your pendulum and the length of the wire, you can actually calculate the acceleration due to gravity in that area. We have to take a couple of things into consideration when we're solving these problems. So as I just mentioned, one, the period is the time it takes to complete one full swing. So for it to start here, to go to this point and to return, that is one full period. Okay, and number two, this formula only works well if the pendulum is held at an angle of less than 15 degrees from the equilibrium position. Okay, as we get further past 15 degrees, errors start to creep in. So this being said, I won't trick you guys and have it like displaced at an angle of 45 degrees. Okay, so just remember these two things as we're solving periods of a pendulum. All right, so example 5, we are determining the period of a pendulum that is 12.5 meters long. So not a whole lot of information, but that's okay because we don't need a lot. Remember, this only really relies on the length of the pendulum and the acceleration due to gravity of that environment. So example 5, we're given the length. So L, that's gonna be my fancy length, is 12.5 meters. And that's all we know. We're looking for the period. So if you look on your formula sheet, you will find one that says period T is equal to 2 pi over the square root of the length of the pendulum divided by the gravitational field strength at that location. So we know length, and we're assuming that we're on Earth here because it does not say otherwise. So we can just go ahead and sub those in. So t is equal to 2 pi over the length of the pendulum, which is 12.5 meters, divided by 9.81 meters per second squared. Okay, if you punch these into your calculator and round to sig digs, you'll get a value or a period of 7.09 seconds. Easy peasy. All right. Cool. Okay, so just 2 examples to go, and then we will be all finished. Okay, so that's how you find the period if you're given the length of a pendulum. Now, in this particular question, we're trying to measure the gravity in a particular location on Earth. So we know the length of the pendulum, and we know the period is 3.33 seconds. We're looking for the acceleration due to gravity here, okay? So we can use the same formula we used last time. So t is equal to 2 pi over the square root of the length divided by gravity. Okay, we are needing to isolate for g. So we just have to be careful as we are isolating for g, okay? So we'll notice that it's underneath the square root. So hopefully you guys want to square this, but we can't just stop at squaring the square root. We have to square everything. Okay, so now this square root and that square will cancel. So we'll be left with t squared is equal to 2 squared is 4. Pi squared, I'm just going to leave that, times the length of the pendulum over the force of gravity. Okay, we can simplify this. We'll just multiply that in. So t squared is equal to 4 pi squared L over g. We're looking to isolate for g, so let's multiply both sides by g. Those will cancel. Now we need to divide by t squared, both sides. So then we will get g is equal to 4 pi squared length of the pendulum divided by the period squared. We know the period, we know the length, and we're looking for g, so now we can just substitute in our values. 4 pi squared, the length is 2.75 meters divided by period seconds squared. Okay, if you punch that into your calculator, you will get a acceleration due to gravity is equal to 9.79 meters per second squared. Okay, so a little bit different than the value that we usually use, 9.81 meters per second squared, but it's close, right? And remember, the force of gravity is going to vary based on your proximity from the center of the Earth. Okay, last question for today. Example 7. So we are trying to find the length of the pendulum that has a period of 1 minute. So t is equal to 60 seconds. So we're going to use the same formula here. So t is equal to 2 pi over the square root of the length times gravity, or divided by gravity, sorry. And we need to isolate for length now. So just like we did last time, we will square everything. Okay, the square root will go away. And we'll be left with t squared is equal to 4 pi L over g. Can't forget the square there. Okay. Now we're isolating for L, so let's multiply by g. Both sides, get rid of the denominator. and then we can divide by 4 pi squared. So if we just rewrite that, so length, now that it's isolated, is equal to gravity times a period squared over 4 pi squared. Okay, so we know G. We're just going to use the G that we've been using for the physics course. We know the period, so we can just substitute those in. So 9.81 meters per second squared. The period is 60 seconds squared. Divide by 4 pi squared. So if we punch those into the calculator and we round for sig digs, we should get a length of 895 meters long. That's a really, really big pendulum. Okay. But yeah, so that is how we can find either the acceleration due to gravity, if we know the length and the period of a pendulum, or we can find the period of a pendulum if we know the length of that. Okay, so the last thing that you guys have to do for today is watch this video. I have posted the link on the YouTube channel. This is just a really good summary of what we've talked about for these last couple days. Okay, so if you have any questions or comments or concerns or anything like that, please feel free to send me a text or an email. I'd be more than happy to help you out. All right, thank you for tuning in, and I hope you enjoy the rest of your day.